ME204, Absolute Motion Analysis of Rigid Bodies. We've looked at rectilinear motion, curvilinear motion, and now rotation of an object about a fixed point, but we haven't looked at what to do when we put all of that together and have general plane motion. Well, when we solve general plane motion problems, there's three approaches that we can take. One method we can use is absolute motion analysis, another is relative motion analysis, and finally instant centers analysis. This time we're just going to focus on absolute motion analysis for solving general plane motion problems. Do you remember this problem from dependent motion analysis? When we solved this using dependent motion analysis, we first started by writing an equation in terms of x and y for the total length of the cable, like we have shown here. Once we have our equation, we took the first time derivative to find our velocity relationships. Absolute motion analysis of rigid bodies follows a very similar process to what we did in this example. Absolute motion analysis relates linear motion to angular motion in order to characterize the general plane motion of the object. There are a few steps that we take for solving absolute motion problems. First, we write an equation relating an angle that changes to a length that changes, and we do this using trigonometric functions, or the law of sines or the law of cosines. Once we have our equation developed, then we take the first time derivative of the function in order to obtain the relationship between linear and angular velocities. To do this, we use the chain rule and/or the product rule that we learned in calculus. Finally, we take the second time derivative of the function in order to obtain a relationship between linear and angular accelerations. And again, from calculus, we use the chain rule, the product rule, and/or the quotient rule to be able to solve these problems. In order to better understand what's happening with absolute motion analysis, let's look at an example. In this case, we're given a 4-foot rod that's connected to two blocks that are confined to specific paths. Block A can only travel in the horizontal direction, and block B can only travel vertically. Let's assume that block A is moving to the left at a constant velocity of 2 feet per second. We want to know the angular velocity, omega, and the angular acceleration, alpha, of the rod when theta is at 20 degrees. Also, let's see if we can figure out how fast block B is moving at that instant. In order to solve these problems, the first thing that we need to do is write our equation relating an angle that changes to a length that changes. In this case, we're going to relate our angle to the length that block A moves to the left. We can see that if A is moving horizontally and B is moving vertically, then our rod forms a right triangle with the paths for A and B. Using this, we can write an equation. A, or our horizontal distance that block A is moving, is equal to 4, the length of the rod, times the cosine of theta. Our next step is to take the first time derivative of the function in order to find our velocity relationships. In order to take our derivative, we have to use the chain rule. We take the derivative of the outer portion of the function times the derivative of the inner portion of the function. And we're going to take this derivative with respect to time. So if we take the first time derivative of our function, the derivative of A with respect to time is equal to 4 times the negative sine of theta times d theta dt. Notice that 4 times the negative sine of theta is the derivative of the outer portion of our function, and d theta dt is the derivative of the inner portion of the function. We can simplify this by knowing that the derivative of A with respect to time is just a velocity in the x direction, and the derivative of theta with respect to time is our angular velocity, or omega. So we simplify the equation so that the velocity in the A direction is equal to 4 times the negative sine of theta times our angular velocity of the rod. If we solve for our angular velocity, omega, then we get omega is equal to negative velocity of A divided by 4 times the sine of theta. Now let's find our acceleration relationships. We take the second time derivative of the function to find the acceleration relationships. So here's our velocity function. The velocity of A is equal to minus 4 sine of theta times omega. We're going to take the derivative of the velocity of A with respect to time. which equals minus 4 sine of theta d omega dt plus omega times negative 4 cosine of theta d theta dt. Again, in order to solve this, we have to use the product rule and the chain rule. For the product rule, we take the first part of the function times the derivative of the last part of the function plus the last part of the function times the derivative of the first. In this case, the first part of the function is minus 4 sine of theta, and the derivative of the last part of the function is d omega dt. For the second portion, the last part of the function is omega, and the derivative of the first is minus 4 cosine of theta times d theta dt using the chain rule. Again, we can simplify this function knowing that the derivative of the velocity with respect to time is the acceleration, and the derivative of the angular velocity with respect to time is the angular acceleration, and the derivative of our angle with respect to time is our angular velocity. So we end up with the acceleration of A being equal to minus 4 sine of theta times alpha, our angular acceleration, plus minus 4 cosine of theta times omega squared, our angular velocity. We know that our acceleration in the A direction is 0 because we're moving at a constant velocity of 2 feet per second. So we can then simplify this equation further and solve for alpha so that we get alpha, our angular acceleration, is equal to minus the cosine of theta times the angular velocity squared divided by the sine of theta. Now that we have our equations, we can go ahead and solve for the different components. If we plug in minus 2 for our velocity, since our velocity is moving in the negative x direction, and divide that by 4 times the sine of 20, we get an angular velocity of minus 1.46 radians per second. For our angular acceleration, we insert minus 20 for our angle, 1.46 radians per second for our angular velocity, and solve for our angular acceleration, which is negative 5.87 radians per second squared. However, we're also looking for how fast block B is falling at this instant. Well, we can figure this out by writing an equation relating the change in B to our angle. In this case, B is equal to 4 times the sine of theta. If we take the derivative of this function, we get that the derivative of B with respect to time is equal to 4 cosine of theta d theta dt, which simplifies to the velocity of B is equal to 4 cosine of theta times the angular velocity of the rod. Knowing that our angular velocity is minus 1.46 radians per second, and that our angle is 20 degrees, we can plug those values into our equation and get that the velocity at B is equal to negative 5.49 feet per second. Let's look at an example where we can use absolute motion analysis as well as relative motion analysis and instant centers to solve the problem. In this case, since we're talking about absolute motion analysis, let's solve this using that method. We have a hospital bed at B that's being raised by moving a roller at A towards the pin at C. If A is approaching C with a speed of 0.5 feet per second, we want to determine the speed at which the platform rises as a function of theta. The 4-foot links are pin connected at their midpoint. Our first step is to write an equation or equations relating an angle that changes to a length that changes. In this case, with our origin defined at C, our x position is equal to minus 4 times the cosine of theta. Our y position, up towards B, is equal to 4 times the sine of theta. Second, we're going to take the first time derivative of the function to find the velocity relationships. The derivative of x with respect to time is equal to a negative minus 4 sine of theta d theta dt, and the derivative of our y function with respect to time is equal to 4 cosine of theta d theta dt. We can simplify these so that the velocity in the x direction is equal to 4 sine of theta times the angular velocity, and the velocity in the y direction is equal to 4 cosine of theta times the angular velocity. Solving for our angular velocity from our velocity in the x direction equation, our angular velocity is equal to the velocity in the x direction divided by 4 times the sine of theta. This can be substituted into our velocity in the y direction equation so that we get the velocity in the y direction is equal to 4 times the cosine of theta times the velocity in the x direction divided by 4 times the sine of theta. Knowing that the velocity in the x direction is 0.5 feet per second, we can substitute that into our equation and simplify so that the velocity in the y direction is equal to 0.5 times the cotangent of theta. Our next topic will be the relative motion analysis of rigid bodies.